Welcome. I'm very delighted to introduce Professor Antonino Di Piazza from the University of Rochester. Even though most people who know him will call him Antonio, and I will call him Antonio. Antonio is a former student in our local master degree program, where he graduated back in 2000.
Yes.
Supervised by Emilio Tordelino. And he then moved to Trieste, where he carried out his PhD in theoretical physics. And then afterwards, he moved to Heidelberg, where he was he joined the Max Planck Institute for Nuclear Physics for a very long time. I think about 20 years or so.
19, yeah.
First as a postdoc, and then as a research leader for a long time. And more recently, I think a couple of years ago, he was appointed for professorship at the University of Rochester. It's a very nice place indeed. Antonio is an international known expert in strong field quantum dynamics and light matter interaction in extreme magnetic fields. We're especially happy to welcome him back to Palermo. Antonio,
thank you.
The floor is yours.
Thank you. Thank you. Thank you for the introduction, Francesca, and for the invitation. So it's a special feeling always to be back in the room where so here I studied quantum mechanics. I was telling Francesca we were facing the professor on the other side at that time. Anyway, so it's very nice to be here. Thank you for coming. So this is the title of my talk, and I go to the outline. So I will give you a long introduction on electromagnetic interaction and on strong field classical quantum electrodynamics, and then I will tell you about the three topics that we work on, namely radiation, pair production, and vacuum polarization. And then something a little bit special is just last slide on NSF Opal, which is a laser system that we are right now currently designing in Rochester. And then I will conclude. So these are some recent reviews, or recent or not so recent reviews in my field. And if you have questions, so you can also have a look at these publications. Okay, so the electromagnetic interaction, so you know that is one of the four fundamental forces in nature, and it is quite unique because it is the only one that has strong consequences both at a microscopic level and at a macroscopic level. So it is, relatively speaking, a weak force, but it has consequences and effects in microscopic dynamics and in macroscopic dynamics. The theory behind it, the relativistic quantum theory, is quantum electrodynamics, and it is so broad in its applications that practically everything that we see around us, except falling objects, practically can be described by means of quantum electrodynamics in principle. If you limit yourself to the lightest particles, electrons and positrons, photons, so the Lagrangian of the theory depends on two quantities, which are the electron mass and the electron charge. And so this means that classically you can construct all the typical scales of the theory by combining these quantities with another quantity, which is a fundamental quantity, which is the speed of light. Quantum mechanically, the dynamics is a bit richer because you have another constant you can play with, and this is of course, the Planck constant. Now, let's start from the energy scale. So the energy scale is determined by the electron rest energy, which is of the order of half mega electron volt to 1 mega electron volt. Now, the momentum scale is not so fundamental as the energy scale, and you obtain it just dividing the energy scale by the speed of light. But it is very useful because it allows one to introduce a very important scale by using the Heisenberg uncertainty principle. You can construct the Compton wavelength, which is the length scale, the typical scale of quantum processes, which is of the order of 10 to minus 11 centimeters. Classically, we don't have anything like that, but if you compute the Thomson cross-section, so the cross-section of a wave impinging into an electron, you see that the total cross-section is proportional to the square of this quantity here, that it is then indicated as classical electron radius. And the interesting thing is that this quantity is 2 orders of magnitude smaller than the quantum scale. So the classical scale, the classical typical scale, so the scale of the less general theory, which is classical electrodynamics, is smaller than the quantum scale, which is the more general theory. So if you go down and down to shorter and shorter length scales, you first encounter the one of the more general theory, which has consequences for the problem of radiation reaction, which I will mention later. Time scale, of course, you just divide by the speed of light, length scale, and you still have these two orders of magnitudes. So what are these two orders of magnitudes? Well, so it should be a dimensionless constant, and it should connect the quantum world to the classical world, so it should contain h bar. And this is nothing but the fine structure constant, which is indeed 1 divided by 137 about, and it contains h bar. Since I work and I will present processes occurring in the presence of strong electromagnetic fields, I have to give you also a scale of the typical fields I'm referring to. These are known as critical fields of quantum electrodynamics or Schwinger fields, and they have this expression here, and I will tell you about their physical meaning in the next slides. I mostly work on processes occurring in strong laser fields, and so for me it is useful also to introduce the critical intensity. So a laser that would have such electromagnetic field amplitude would have this critical intensity, which is of the order of 10 to 29 watt per square centimeters, and it exceeds by about 6 orders of magnitude what we can do nowadays in the lab, but this is not a real limitation, as we will see in a few slides. Okay, so in order to understand the physical meaning of the critical fields, I have to tell you something about the quantum vacuum. So quantum mechanically, the vacuum state is the lowest energy state of the theory, where no particles are present, so no electrons, no positons, no photons. However, we have this pictorial view of the vacuum as being populated by what we call fluctuations, which are exactly, so pairs of particles and antiparticles like electrons and positrons, which spontaneously pop up in the vacuum, and they annihilate again without leaving any trace in the vacuum, after covering a distance which is of the order of the Compton wavelength, and after a time which is of the order of this Compton time which I have introduced before. How do we arrive to this idea of the vacuum fluctuations? Well, quantum field theory, in general, or QED in particular, they were formulated originally to combine quantum mechanics and from one side and special relativity. Now, from quantum mechanics, we have this sort of time energy uncertainty principle, like that says that in order to measure energies with an accuracy of the order of delta epsilon, you need a process lasting a time delta t according to this Heisenberg-like uncertainty principle. On the other side, you know about the equivalence about mass and energy, and therefore it is not surprising that a theory which combines these two theories allows for the existence, the ephemeral existence in such a short time of these pairs according to Heisenberg uncertainty principle. Now, if you look at the expression of the critical field, you see that you can write this equation here, which means that the critical electric field is able to transfer to an electron or to a positron on a Compton wavelength an energy of the order of mc squared. So this means that if this is a vacuum fluctuation and you set there an electric field of this order of magnitude, before the pair annihilates back, the field is able to transfer an energy that corresponds to the rest energy of this pair. So in other words, it is able to make this pair real. In other words, the vacuum under such a strong electric field should become unstable under electron-positron pair production. Exactly, so this is what I just said. Now, the magnetic field, in the presence of a magnetic field, static magnetic field, of course the vacuum is stable, independent of how strong is the field, because the field cannot transfer energy to the charges. And the physical meaning is instead given by this equation here. This is the magnetic moment associated to the electron, associated to the spin of the electron, and this is the magnetic energy associated to the critical field, and again is of the order of mc squared. So then in the presence of background electromagnetic fields, which are of the order of the critical ones, we have a new regime of QED, which we call the strong field QED regime, where the properties of the vacuum are substantially altered by the fields. For example, it becomes unstable, but we will see also the dielectric properties of the vacuum are changed. There is a tight interplay between collective effects, so plasma-like effects, and the quantum effects, because once you produce an electron-positron pair, this is accelerated inside the field, and these pairs produce photons, which then can also decay in the electromagnetic field, and they produce other photons into an avalanche of so-called QED cascade, which I will discuss also later. And then it is inaccessible to conventional accelerators in the sense that you need a coherent field to prime this kind of effects, whereas in conventional accelerators, you typically have the collision only of two particles. Yeah.
I said this argument are very qualitative so far. So
yeah.
But so should we understand the field in this setting as
classical field?
Oh, okay. Even though, I mean, they are interfering with a quantum environment.
It is right. Yeah, this is a pictorial view. So if one then goes into the details, so if one then starts asking questions, then you see that there are problems like, for example, the density of these particles is infinite, is not infinite. So you start getting into troubles. And later I will say something a little bit more rigorous on this. Okay, so then focusing more on on strong field QED in the presence of an intense laser field, I consider a sort of experiment, theoretical experiment, let's say, where you have a single electron that collides with a laser that I approximate with a plane wave. So I characterize it by means of two numbers, which are the frequency and the amplitude. And the electron is characterized by the energy. And now, typically in this field, the quantum electrodynamics is a Lorentz and gauge invariant theory. Also, the physical observables must depend on quantities which are Lorentz and gauge invariant. Two important parameters in this field are known as psi and chi. So the first one is actually a classical parameter, so there is no h bar. And as you can see, it corresponds to the work that the laser does on an electron or a positive laser wavelength in units of mc squared. So this means that if this parameter is larger than unity, the system is intrinsically relativistic. So if the electron would be at rest inside this plane wave, within half a period, it would become already relativistic. And the Lorentz force, so the V cross B force, becomes of the order of the electric force, and then all nonlinear effects start becoming important. But you can write this by multiplying and dividing by h bar. You can also write this in this way and interpret it as the work done by the electric field on, again, electron or positron, this time on the typical quantum length, so on the length of quantum processes, and in units of the energy of a single photon. So it means that if this quantity becomes larger than unity, multi-photon effects are important. So the laser is able to transfer during a quantum process an energy which corresponds to many photons. So you have multi-photon effects. The other parameter is a quantum parameter, and it tells you why the fact that the critical electric field is much larger than what we can produce nowadays in the lab is not a real limitation. The point is that in such an experiment, from a theory point of view, what matters is what the electron experiences in its rest frame. So if you collide an ultra-relativistic electron with a plane wave, the field that the electron feels in its rest frame is boosted by a factor of gamma, of the Lorentz factor of the electron. And then even if this ratio here is much smaller than unity, you can compensate and by means of a gamma factor larger than unity. And so what matters is this parameter is so-called quantum nonlinearity parameter. And if this parameter is larger than unity, pure quantum processes, so quantum effects, are important, like, for example, the recoil that the electron experiences when it emits a photon, or entire quantum, so pure quantum processes like the decay of a photon inside a laser field which has no classical counterpart. And so in some sense, we are interested in this regime where both these parameters are larger than unity, and this is what we call the strong field QED regime. So now, can these parameters be made larger than unity currently? So let's see what we can do from a technological point of view. And I limit myself to optical laser technology because it is in the optical regime where we can produce the highest intensity lasers. So entire experimental campaigns, like for example in UK, or this is at Corels in South Korea, so have been carried out already at intensities which are of the order of 10 to 20 watt per centimeter square. There are already facilities which can reach intensities of the order of 10 to 21, 10 to 22 watt per centimeter square. And as I have already mentioned, the world record intensity is of the order of 10 to 23 watt per centimeter square. But in this case, they didn't do an experiment. So they just obtained this intensity without doing an experiment, which is a different thing. Of course, to do an entire experimental campaign, so you have to take care of stability and things like that. Future facilities, like the one that we are currently developing or designing in Rochester, they will exceed present intensity by a factor of 5, maybe. But as you can see, we will stay below this Schwinger intensity, which is of the order of 10 to 29 watt per centimeter square. So we need, in order to enter this strong field QED regime, we need a high energy electron beam. Now, conventional accelerators have reached intensities, energies of the order of 50 GeV. For 50 GeV, the relativistic factor is of the order of 10 to 5, which is a very large number. However, conventional accelerators are usually big machines and difficult to combine with lasers. However, there is a new technology which now is no more so new, is several years. That is it's called laser wake field acceleration. So you can use lasers also to accelerate electrons, and you can reach lower energies of the order of 10 GeV, and you essentially shine a laser on a gaseous target, and you generate a wake which pulls the electrons a little bit like water waves on the sea. The electrons can be pulled to energies of the order of 10 GeV, but the quality of these electron beams are not so good as those of conventional accelerators, of course. But the advantage of laser plasma accelerators is that in a laboratory where you have a big laser, you can split the laser beam, and you can use part of the beam to accelerate the electrons, part of the beam to produce the large high field, and then you have an intrinsically synchronized system, which is an advantage. There are also two experiments, one in Germany and one in the US, in California, which where there are two X-free electron lasers, so there are high energy electrons already available, and people have built there also lasers, not so powerful, and these two experiments, they aim at, since they use high quality electron beams, they aim at measurements with high precision as those compared to those based on laser plasma accelerators, which are not so accurate, actually. Yeah.
Not about thinking. I don't understand why. So if you put the electrons in the field, then
It's not a vacuum, yeah.
okay, so then now you can move up and experiment to do. So I thought you were trying to put that reduction to then I'm getting lost with.
No, this is a little bit of a different setup. This is a little bit of a different setup. I will come back to the vacuum later. Now here, so typically it is easier. Hmm? So in the vacuum, let's say you would need a field which is really of the order of the Schwinger field. So, no, not really, because so there are slightly different processes then.
Also, you mentioned in your presentation that the critical field should be at the order of 10^16. I think, as far as I remember, you need to apply some 10^18 volt per meter.
Right, which is 10 to 16 watt per centimeter. Centimeters, yeah. So yeah, there's units sometimes. So if you plug some numbers into these parameters, you see that with current technology, the optical lasers have energies of the order, photon energies of the order of 1 electron volt. So you see that at current intensities, you can easily exceed Xi, values of Xi of the order of unity. In fact, nowadays you can also have 10 or 20. However, it is more difficult for the parameter chi. So you need, oh, it's gone. We should tell Francesco to take another laser pointer. No, it's not working. But okay, so I think it's the battery could be. Well, I can continue like this, and Angelo has one. Maybe. Francesco had one. Francesco had one. I think so.
Charging this while you are speaking.
Hear me?
No, ma non vorrei che interferisse con,
con
quello che già sta utilizzando.
Non ti avevo riconosciuto quando sei entrato, sei abbronzato. Aspettiamo Francesco.
C'è una versione
Dice analog. Cioè, se vuoi produrre coppie dal vuoto, diciamo, hai bisogno proprio del campo di Schwinger. Se parti con una particella che ha già un'alta energia, quindi che può anche contribuire in termini energetici, allora puoi abbassare il threshold. It is not called Schwinger per production, but there is per production, but you have some matter already in the system, so to speak.
The model is like some classical stuff plus coupling, like
yes.
Mechanics.
Yeah. You have the Lagrangian of QED plus one term where with the electrons interacting with the background field. Yeah. So it is a QED in a background field, essentially. Okay. So let's start with the first process I wanted to discuss with you, which is nonlinear Thomson scattering or Compton scattering, depending on whether quantum effects are important or not. Because, of course, this process is also a classical counterpart, right? So you have an electron inside a laser field. It can absorb quantum mechanically many photons from the laser and emitting a single energy photon. Classically, we would interpret it as the electron being accelerated by the laser field, so it is an accelerated charge, and as an accelerated charge, it emits radiation, and this radiation is Doppler boosted, because the particle is the electron is highly energetic. And so you obtain high harmonics of the field. Quantum mechanically, you interpret this in this way. So the electron can absorb, since the laser is intense and so the density of photon is very high, it can absorb in a single shot, it can absorb many photons and emit only one single photon, a little bit like in high harmonic generation in vacuum. Is a similar process in atoms. Now, the nonlinear effects or multiphoton effects, as I have already mentioned, they depend on the parameter psi. Okay? The importance of quantum effects, so the importance of recoil, as I have already said, as we will see, depends on the other parameter. The main quantum effects are two. The stochasticity, which means that radiation is not like we say in classically radiation is a continuous process. So the electron continuously emits electromagnetic waves. It is not a continuous process, but a discrete emission of quanta, which are called photons, so in lumps. And then the recoil. The recoil is, since photons, as any other particle, have energy and momentum, when they are emitted by the electron, they carry their own energy and momentum, which is taken away from the electrons, which undergoes a recoil. Okay, so in this consequence of this is that classically the electron can emit frequencies which there is no an upper limit theoretically on the frequencies that can be emitted by an electron classically. Quantum mechanically there is a limit because the energy cannot exceed the energy of the electron. And this reduction implies a reduction also of the average emitted. So quantum electrodynamics predicts that on average the electron emits less than the classical prediction. So how can we understand qualitatively why the effect of recoil is controlled by the parameter chi? So we said that the electron can absorb Xi photons from the laser. So you start with Xi photons, and each photon has an energy h bar omega L, but it is twice Doppler boosted, because if the electron goes against the laser, so you first go into the rest frame of the electron, and you have the first boost, and the electron emits, let's say, isotropically. Then you go back in the laboratory frame, and so the photons that are emitted in that direction are again boosted, so you have another factor of 2 gamma. And if you combine all these quantities here, you obtain exactly the chi parameter times epsilon, which is the energy of the electron. So the ratio of the typical energy emitted by the photon, by the electron, and the electron energy is of the order of chi. So the importance of the recoil is determined exactly by chi. And now, related to the problem of radiation, there is an old problem of radiation reaction, which indeed I studied already when I was in Palermo, both with Emilio Ferdilino, and a little bit, which is the problem of radiation reaction. If the electron radiates while it is accelerated inside the laser, of course it loses energy and momentum, and you have to take into account this if you want to determine exactly the electron dynamics. So first of all, non-relativistically, it is clear that an accelerated electron emits energy. So the energy per unit time is given by the famous Larmor formula that you can write in a relativistic form in this way, and this minus sign here is only because I use this metric, and it is a Lorentz invariant quantity. So no inertial frame has doubt on the energy emitted per unit time. This is what I said. So if you want to determine the exact dynamics of the electron, you have to take into account this energy and momentum loss during the evolution inside the external field. And now I don't have time to go into the technical details, into the derivation of this equation, that essentially what these people have done, and as you can see from the names, is an old equation. So these people have added to the equation of motion of the electron inside an electromagnetic field, which is the Lorentz force equation, they have added an additional force called the radiation reaction force, because it is due to the radiation emitted by the electron. So it is a reaction of the radiation emitted by the electron on the electron dynamics itself. And now, exactly, without going into the details of the derivation, you see that this last term here is exactly the Larmor formula with the opposite sign. So it is a real damping term. The variation of the velocity is proportional to the energy emitted per unit time times the velocity of the electron itself. So it is a real with the opposite sign. So it is a damping term. But then there is this other term here, which is called the shot term, which must be there. It must be there from a theory point of view, because any four-dimensional force has to be perpendicular to the forward velocity of the electron, because otherwise the relation between energy and momentum would change. So this has to be perpendicular in a four-dimensional sense to the forward velocity. So this term must be there. But this term is very problematic, and this is why we are still discussing this equation. It is problematic because, as you can see, it depends on the derivative of the acceleration of the electron. So it is an equation which is a third order differential equation, which is already strange because Newtonian dynamics is typically two-dimensional, so two second order differential equations.
The question is an out result, or
Yeah, this was derived first by Lorentz and Abraham, and then again by Dirac.
so is it taken into account of recoil or recoil?
Without recoil. Because also classically, if the electron emits radiation, radiation has some energy, right? So electromagnetic wave.
Recoil is just
This is a sort of classical recoil, if you want, sort of. In fact, there should be a way, and there is a way, of deriving this equation from quantum mechanics. But exactly on this derivation, you see relativistic. This is relativistic, yeah. But first, let me tell you the problems of these equations. The problems are the existence, so the fact that this equation allows for existence of so-called runaway solutions. And there are other problems, but runaway solutions are in some sense easier to see, because if you take the non-relativistic limit, you see that even if you don't have any external field, you have this equation here that admits not only the solution that we would expect, that is V constant velocity, no fields, but it also admits this solution where the acceleration exponentially increases in time. But let me notice the following, that the typical raising time is exactly of that order of magnitude, of that classical time, that is below the quantum scale. Right? If you remember what I said at the beginning. So this means somehow that these effects are on certain time scales where quantum effects already should be important. And this was a remark that Landau and Lifshitz noticed in their book on classical electrodynamics, so the second volume of the series, where they noticed that if you ignore all quantum effects, which is what you are doing here because you are considering classical electrodynamics, you can show that in the rest frame of the electron, this force here is always much smaller than this force. And therefore, you are allowed, if you already neglect quantum effects, you are allowed, wherever you see the for acceleration in this force, you can replace the zero order for acceleration, which is given only by the Lorentz force. And if you do this in a consistent way here, you end up with this equation, which is known nowadays as Landau-Lifshitz equation. And this equation, as you can see, of course, by construction, has not the shortcomings of this equation, because if the external force is zero, the acceleration is zero. It is a second order by the way you constructed it. And this is an equation that people are trying to test experimentally. These are experiments that have been carried out to test this equation here. There are some indications that it's okay, but the problem in these experiments somehow is a little bit ironic, is that the laser intensities are so high that quantum effects are important, and then you don't really, this equation does not hold, but it holds with some quantum corrections, and then they are not really clean experiments. You say, okay, you can reduce the laser intensity, but if you reduce the laser intensity, also these effects become smaller and then becomes too small to be detected. So it's a little bit intermediate regime, difficult to catch experimentally. Quantum mechanically, how do we interpret radiation reaction? So in general, it is difficult. It is difficult because the point is that when the electron emits radiation quantum mechanically, this radiation can interact with the laser itself. And so you can produce other electron-positron pairs, and then you don't have anymore a single particle dynamics. So you start with one electron, and you end up with a shower of electrons and positrons, so you lose track of your initial electron, of course. But if you work, so we notice that if you work in this regime where the quantum parameter is not so high, you can already have quantum effects, but still per production is negligible, so you don't have this problem of the showers. And essentially the radiation reaction corresponds to account for multiple sequential emission of photons by an electron. So the electron cannot emit only one photon, but 2 photons, 3 photons, and so on and so forth. And so we noticed with this student of mine that if you do, we did some numerical study with this quantum parameter being a little bit less than unity, but we already saw some quantum effects. In particular, we wanted to show the importance of stochasticity. So of the fact that radiation is not is a stochastic process and not a deterministic process. And so we considered the collision of an electron bunch with a laser with this intensity. And so this is the energy distribution at t equal to 0. And then after the evolution inside the field, you see that the electron bunch energetically becomes more spread because you have this stochastic effect. But if you do the classical calculation, you have that the electrons with more energy radiate more than electrons with less energy. So the classical prediction is actually that the energy width becomes smaller because it is deterministic. So classical and quantum predictions are really the opposite to each other. So it is very, very important. We also consider the semi-classical model where you can modify the Landau-Lifshitz equation, taking into account of what I said before, that quantum mechanically you have a reduction of the average energy emitted, and then in this way you have so less radiation, so the shrinking of the energy width is less than for pure quantum, for the Landau-Lifshitz equation, but still you have a shrinking of the energy width. So in fact, the broadening, we show that it is due really to the stochastic nature of the radiation. Okay, so now I pass to another process which instead has no classical analog. So it is one of the striking, indeed, predictions of quantum field theory, which is the fact that electromagnetic fields can transform or can produce matter out of light, essentially. This was a prediction that Dirac did pure based on theory considerations, and then Anderson verified experimentally. 2 photons that in their center of momentum frame have a total energy larger than 2mc square can in principle transform into an electron-positron pair. What happens if you have a high energy photon and a laser which is intense? So it contains many photons, but these photons have energies of the order of 1 electron volt. So 1 million times smaller than the mass of the electron, let's say 500,000 times smaller. So it can happen also in this case that the photon collides with the laser field, and pairs absorb a large number of laser photons in such a way that even that in the center of mass of the sum of all these photons, again you reach the threshold to produce an electron-positron pair. Let me tell you how this works qualitatively again. So if you consider this high energy photon with energy h bar omega, and again you can absorb order of psi photons from the laser, and you want that the energy in the center of mass of momentum is larger than mc square, you end up with this condition on the laser intensity, and here you can recognize essentially the same parameter as for the electron, because instead of the energy of the electron here, there is the energy of the photon. So you have what we call the quantum nonlinearity parameter, but for the photon, not for the electron. And this shows that the controlling parameter is a sort of quantum nonlinearity parameter for the photon. The interesting thing is that is the behavior of this, the probability of pair production for low fields. Because in the case of nonlinear Compton scattering, if you do the limit of no quantum effects, so you do the limit of h bar going to 0, you have a classical analog for radiation, of course, because classically electrons radiate. But in this case, you have this peculiar dependence on h bar here on the denominator. So you have a non-perturbative dependence on h bar, and of course the probability goes exponentially to 0, and there is no pair production classically. So it's a pure quantum effect. Related to this is a problem of QED cascades. So QED cascades is an interesting topic that it has been studied and developed lately. The idea is that you have two laser fields that collide one against each other, so they produce a standing wave. And in the middle, you have even a single particle, even a single electron or a single atom that is almost instantaneously ionized. The Bellenkirch found that if the laser intensity is of the order of 10 to 24 watt per centimeter square, this electron, this seed electron here, would be so strongly accelerated that it emits so high energy photons that then decay into electron-positron pairs, so what I mentioned at the beginning, that produce other photons, and then you create a sort of plasma of electrons and positons and photons, where you have this kind of collective and quantum effects, which I mentioned at the beginning. In order to see this a little bit in terms of what we said before, you should imagine that you have this electron between two waves. One wave pushes the electron against the other wave, and then you have a process, so the electron becomes ultra-relativistic, it hits the other wave, it is accelerated, it produces photons, and they decay into electron-positron pairs. So it is all, in some sense, related. By one order of magnitude. So nowadays the record is 10 to 23. We are not very far. Yeah. In fact, at NSF Opal, where we will have 5 10 to 23, we already see some from numerical simulations. We see some indications, but there are no. So in order to talk about a cascade, people want to see an exponentially growth of the particles, and this is still not enough. In this case, electrons and the positons. Yeah, and you want to see an exponential increase of the number. So finally, last topic is again related a little bit to the vacuum. So classical Maxwell's equations, you know, in vacuum they are linear equations, right? So this means that if you have two electromagnetic fields, they just superimpose each other. They don't talk to each other. Superposition principle holds, and the system is linear. But due to the presence still of these vacuum fluctuations, two photons can in some sense hit one of these electron-positron pair, and then this electron-positron pair can mediate a quantum interaction between photons. So a process of photon-photon scattering can occur in vacuum. As I have said at the very beginning, this process is not local because the pairs leave for or cover a distance of the order of lambda Compton. So in general, it's not local. But if this, the wavelengths of these colliding photons would be much larger than the Compton wavelength, then of course they don't notice the Compton wavelength, it's too small, and then the interaction is local. And then you can write down what is called an effective Lagrangian approach. And this effective Lagrangian approach holds for wavelengths much longer than the Compton wavelength, which means for photon energy is much smaller than mc squared, which is quite easy if you collide optical or even X-ray photons. So this approach is quite wide in its applications. So since this interaction is a 4-photon interaction and it is local, it can be described by a correction. This is the Maxwell Lagrangian. It is quadratic and gives rise to linear equation. Once you derive from the Lagrangian, you do a derivative, right? So you from quadratic to linear equations. This is quartic because there are 4 photons interacting. And this is the first quantum correction. So, and people nowadays try to study the consequences of this correction. You can also see this in a slightly different way. The vacuum as being populated by these fluctuations, and these fluctuations, since there is the electron from one side and the positron from the other, are like small dipoles that when there is no field at all, they are randomly oriented. But if you put, for example, an electric field, then you can orient them, you can polarize the vacuum, as we say. And then one of the effects, one of the interesting effects is this. So imagine that you have 2 waves polarized in perpendicular directions. If they propagate in the vacuum, let's say, then of course, as we know, they have the same speed, which is the speed of light. But if you propagate them in the presence of another field, which polarizes these pairs, you see that they have, depending on whether the probe field, so on whether this field is polarized along this polarizing field or perpendicularly, the speed is different. So you can calculate analytically the refractive indices of the vacuum. The refractive indices of the vacuum have this general expression here. You have 2 possibilities, namely if the probe is polarized in this way, where E and B are the electric and magnetic field of the background field. And you see that if it is polarized in this direction, the expression is this. The expression is this. They are the same except these 4 and 7. So you have a birefringent medium. So if you would polarize an incoming field in a direction which is between these 2 perpendicular, so it's a linear combination of the 2, you start from a linearly polarized field, and then the 2 differ because of the different refractive index, and you should observe ellipticity. So there are various effects that have been predicted based on this, like so effects that occur in materials, in solid states. They could, in principle, occur also in vacuum. So like laser self-focusing, since if you focus, for example, a Gaussian beam and you send photons in these directions, since the refractive index is larger here than here, due to the Gaussian shape, you should observe self-focusing. None of these effects has been ever measured in experiments because you need too high intensities. This is something that we did many years ago. That is light by light diffraction. So you send an X-ray probe against a standing wave, and you should see that this piece behaves like a small piece of material, and it would diffract. In some sense, you can ask yourself the question, does light produce shadow? Okay, so this was, let's say, the more scientific part. This is a little bit more, so talking about what we are doing really in Rochester. So NSF, which is the National Science Foundation, has funded us with $18 million to design this laser, which is called NSF Opal. The scientific program is divided into 4 areas. One is laboratory astrophysics. So you try to reproduce in the lab conditions which are, for example, inside planets, large planets, or astrophysical conditions. Another one is laser-driven nuclear physics. So you try to do, for example, experiments with high fields in and nuclei. Each of these areas has a co-PI. I am the co-PI of the high field physics and quantum electrodynamics, which is what we discussed so far. And then there is another area, which is the particle acceleration. So to use fields, laser fields to accelerate particles to very high energies. So we predict that we could reach even 100 GeV electrons. So this laser should be constructed at the LLE. That is where I also work. So these are already existing buildings. Sorry, this is a laser already existing at the LLE, and this is the new building which should host this facility. So this facility is schematically is made of 2 lasers that are produced by the same front end. They are split at one point, and then they are amplified to 25 petawatt, which this would be the highest power, the most powerful laser in the world. So we would have 2 beams of 25 petawatt, and in the same target area, we would have also the beams already existing from another laser called Omega EP that would also go into this area. They would be useful for experiments like for laboratory astrophysics. So it would be a very versatile facility, unique really in the world. But so far, NSF has only funded the design. The whole facility should cost more than $270 million. So it's a very big facility, and at the moment, as you know, there are other problems in the US than lasers. Okay, so conclusions. So I hope that I convinced you that lasers, modern lasers, high-power lasers, they can offer unique possibilities to test quantum electrodynamics in regimes which cannot be tested with accelerators. I have given you some examples of processes like radiation, electron-positron pair production, or the nonlinearity, the dielectric nonlinearity of the vacuum. And then finally, if you want to help us, you can sign this is a letter of support. It's nothing special. So if you click on this QR code, you can sign a letter of support, because NSF, of course, said for such a big facility, you need to show that the world would benefit, the entire world would benefit from this facility. And so if you have time and you wish, you can help us with this letter of support. Thank you.
Vacuum polarization. So it's only intensity of the field that dominates, that determines pressure, and also wavelength out of it.
The wavelength, so
you saw that like if it's too small, so if you go into the long, short wavelength calculation, but I can like a diagram with the square like that.
So if you consider, in this case, for example, we used an X-ray probe because you see, so like if the refractive index The refractive index does not depend on the frequencies. But if the refractive index does not depend on the frequencies, things like ellipticity, so the phase differences, of course, are larger for higher frequencies. Well, you have larger effects.
So there is also, if I have to think, from this if I can say that it's like a material.
Yeah, by refringent medium, yeah.
It should have a dependence on the frequency.
Yes, this you have this if you go into a regime where this square is not negligible anymore,
Okay.
because then you can see, yeah, then you can see frequency effects. Otherwise, it's just a constant refractive
But
index.
in that case, you have to go to like an ultra high.
Gamma rays, yeah. If you want to see the box, let's say. Yeah.
There is a question. So, when you discuss the you said it's completely stochastic, but in terms of, let's say, the statistics of the photons themselves, there's no any effect that branching, whether you are basically emitting inside already strong field, so the photons will be strongly influenced by the fact that
Right.
you want to go towards the same direction.
So if the electron is ultra relativistically, usually it's the electron that determines the direction of emission. Because you should imagine if the electron has a GeV energy and the photons of the laser have 1 electron volt energy, even if you absorb, let's say, millions of photons, which is the case, it can be the case, but you still have 5 GeV against 1 MeV. So the directionality is determined by the electron still. But there are situations, and people have studied this, where you use lower energy electrons, and then you can compensate. So the laser can push back the electron, and then the directionality is also strongly determined by the laser. What the laser does is that if the laser is polarized like in this direction, so like if the laser is polarized in this direction, when the high energy electron arrives in this direction, then the radiation has an ellipsoidal, elliptical emission, because along the polarization direction, the electron oscillates like this, and so along the direction, usually you have a larger angle than in the perpendicular direction. So, like if this is the electric field, and this, oh, I don't know, the magnetic field. So along the magnetic field, the angle, the aperture angle is typically 1 over gamma, where gamma is the gamma factor of the electron, whereas in the longitudinal direction, along the polarization direction, the angle is xi divided by gamma, where xi is this other parameter. So it's longer, for xi large is longer, is elongated.
Can you go back to your slides where you mentioned standing wave stuff?
Yeah.
Actually, I'm also working in this field. I'm a bit of interested in this competitivity. So let's think about a hypothetical situation. You have lots of many atoms, and then
so many atoms inside the laser.
Yeah. And then we pump like use two counter propagating pump. So you have a spatial modulation, some first square of sin square kx minus.
Right.
Then we use this swinger pair production rate, some p square times this critical that you saw, no, e exponential critical minus some modulus. So then we generate the standing wave. Can we treat as a like solid in vacuum?
So if you have already atoms, with the Schwinger formula, you can consider the situation where you don't have atoms, and you have the standing wave, and then you can use the Schwinger formula with the standing wave. This you can do, and it will give you the per production rate. But if you have the atoms, you have to take into account them, and before you have Schwinger per production, you have this mess, so to speak, because you ionize.
So like we apply the pump, then we generate the density, and then we rule out the possibility of like pump. Like we have to calculate HHG. That should give you the signature of solid nature, like some peaks. Then there is a plateau, and there's a direct cutoff region, something like that. So after this generation of the standing wave, can we treat as solid so that we can use the density for the like probing the system.
I'm not sure that I understood your question, but so the problem of treating this as solid is that the laser is so intense that the matter is completely ionized.